Hello, everyone. My name is Mingyu Liang. I'm a PhD candidate at George Mason University. Today, I'm very happy to present our paper, Epsilon Delta Indistinguishable Mixing for Cryptocurrencies. This paper is a joint work with Ioanna Karantaidou, who is also a PhD candidate at George Mason University, as well as Foteini, Baldimtzi, and Dolph Gordons at George Mason University, Mayank Varia at Boston University. The anonymity issues of cryptocurrency is well known for a long time. Many classical implementations, like Bitcoin, it's only pseudo-anonymous and the transactions are quite linkable. In particular, addresses belong to the same user can be distinguished and even re-identified by analyzing the transaction pattern with the right auxiliary information. To tackle such issues, there are many efforts on breaking the linkage among the addresses. One classical idea is to use a mixing mechanism. Specifically, multiple users each have their coins stored in a potentially identified address, mix their coins together and deposit them into newly generated addresses. In the end, an anonymity set is formed among the participants. Clearly, the larger the anonymity set, the better the privacy each participant enjoys. Such mixing mechanism can be implemented with an untrusted third party or relies on decentralized techniques. One example for Bitcoin is CoinJoin, which allows transaction with multiple inputs and outputs. However, the maximum size of a transaction that can fit into a single block limits the maximum size of the anonymity set. There are also standalone cryptocurrencies with built-in privacy guarantee. And two of the most successful ones on the market are Monero and Zcash. Monero transactions use ring signature to hide the real inputs of the transactions among a small numbers of other addresses. For Monero, there is also a limit on how much address you can roll in. By default, each transaction only has 10 mixing, and the computation cost is linear to the number of mixing. On the other hand, Zcash relies on zero-knowledge proof for its juicy transactions to completely hide the input and output of a transaction. While this gives the strongest possible privacy, the current implementation requires trust setup, and it is less efficient without it. As a result, our goal of this paper is to build a solution that offers formal privacy guarantee and security under composability. And it should accommodate very large anonymity sets, for example, n greater than 1,000. Ideally, the solution should not require trust setup or any untrusted third party. And last but not the least, it should have sub-linear computational cost per party so that it's scalable. How do we do that? We do that by allowing some control to leakage. To achieve our goal, we start by using ring signature-based transaction to create an anonymity set of small size. Consider the example of 3 user mixing on the right. Each user owns a potentially identified input address at the top layer and need to transfer their value to a freshly generated output address at the bottom layer. To obfuscate, each user additionally rope in the other input's address as mixing, thus hiding the real spender of this transaction. However, naively extending this to n-size anonymity set is costly, as the computation cost per party is linear to the number of mixing in each transaction. Instead, to achieve a large anonymity set, we use butterfly network to augment the smaller one we just introduced. This is a 2-array A-size butterfly network. A-size refers to the A nodes in any layer. 2 arrays means that for every node except those in the bottom layer, it collects to 2 nodes in the layer immediately below it. And this collection can be decided from drawing the repetitive butterfly patterns. When we use the butterfly network, the top layer nodes correspond to the input address of the mixing users, and the bottom layer nodes correspond to their newly generated output addresses. Note that between any input node and any output node, there is a unique path. Now, let's consider an even simpler four-side butterfly network and see how we use it for four-party mixing. In this case, user 1 and 4 would like to pay directly to the new address we know, while 2 and 3 basically swap their output position. To transfer one's values from its input address to its output address, each user follows strictly the path defined by the underlying butterfly network while creating additional addresses in the intermediate layers to forward their values. Clearly, there could be collision of paths, so we are using buckets instead of nodes for the junctions in the intermediate layers. Currently, the transaction graph is clearly non-private, and our first step is to make address residing in the same bucket indistinguishable. To achieve this, we use ring signature-based transaction to create small anonymity sets. Specifically, we make sure that all transactions that goes in and out of the same bucket includes the other collected inputs X mixing. In the end, the address in each bucket became indistinguishable from each other. The remaining leakage can be captured as the number of addresses within each intermediate bucket, or simply the bucket nodes. Note that this remaining leakage does tell something about the permutation. For example, if we instead use an identity permutation, then the intermediate addresses are evenly distributed among all buckets. To resolve this final leakage, we randomize the leakage by adding noise. Moreover, to avoid excessive amount of noise, we borrow the elegant idea from differential privacy, and we only require enough noise to obfuscate any pair of labeling permutation rather than any arbitrary permutations. Formally, we say that two permutations are labeled if they differ in a single swap. Intuitively, by providing obfuscation for any pair of labeling permutation, we give any user alibis to claim any output address as its own. Note that in the example we just had before, a single swap of party 3 and party 2's output address caused the intermediate bucket nodes to change. To hide the difference of bucket nodes, we sample a certain number of noisy addresses for each bucket. On the left, we have the two intermediate bucket nodes corresponding to the previous example. And on the right, we add some number of noisy addresses for the nodes corresponding to the first case. And we enforce the same rule for all the noisy addresses within the buckets on roping in mixing so that they are indistinguishable with the real address. We also use confidential transaction to hide the transferred value, as the transactions involve noisy address should contain 0 value. Now, since these are just noisy nodes, then this particular view is a possible leakage for both permutation. Formally, we show that our mechanism achieves epsilon delta indistinguishable mixing, which requires that for any labeling permutations, the distribution of their leakage should be closed and bounded by a multiplicative factor of e to the epsilon and an additive factor of delta, similar to the definition of differential privacy. In practice, the noise in each bucket can be sampled from negative binomial distribution, which allow us to evenly divide the noise sampling responsibility to each user in the protocol. We give a syntactic analysis of our protocol using butterfly network with different arrays and compare them to the naive case of creating n-size anonymity set with ring signatures. Compared to the linear computation cost in the naive case, our protocol requires square root of n when the square root of n array butterfly network is used. And if we use 2-array butterfly network, we can further reduce it to log to the power of 3n. But for the values of n that we are interested in, square root of n every butterfly network, it's actually more practical. Therefore, we conduct experiments measuring the computational cost of ring signatures with different privacy parameters. Clearly, the better the privacy parameters are, the costly the computation is, as we need to add more noise. For conclusion, our protocol have the following strengths. First, our computation type per party for n-party mixing is O polylog n. We offer smooth tolerance of failed-store adversary. If a party aborts, it slightly reduces the privacy, but the protocol can continue without any specific action. We do not require any trust data, and our construction is UC secure. For weaklists, we do not provide full anonymity, but rather bound the leakage using the definition of epsilon delta indistinguishable mixing. As with all mixing protocols, we can only mix address of online parties. And that's all for the presentation, and I'm very happy to answer any questions.